to, we can differentiate them. You already know how to calculate the differential of a zero form. That's the total derivative that we teach you in Calculus 3. You already know that. You already know how to exterior differentiate a function. It is the total differential. Notice that you start with a function and you output a what? A one form. So the total differential changes object type. Start with function, differentiate, get one form. That is why it's an exterior derivative. You're starting with one type of object and you're ending with a different kind of object, right? So in fact, you've added one to the form degree. So the exterior derivative of a function is simply the total differential. You know this already. Now, my question is, if you put together this new idea we just discovered, the work form correspondence, what does that have to do with the total differential and things you already know in Calculus 3? This is the work form correspondence of what vector field? This is the work form of which vector field? I'll write it out. See, this is the work form of the vector field partial xf, partial yf, partial zf. If you'll allow me the abbreviated notation, which I love. What is that? That has a name. Nobody? Surely somebody remembers the name of this from Calculus 3. What is this vector field with relation to the function f? F is a function, this is a vector field, what's it mean? We have a notation for this, it's what? Some books might use grad. I prefer nabla. So this is, of course, the gradient vector field. The gradient vector field is so the exterior derivative automatically calculates the gradient vector field for a function. Next up, how do we define the exterior derivative of a, like a one form? So if you have d omega, ABC, let's say, the way this works is you do dA wedge dx plus dB wedge dx plus dc wedge dx. So the way the exterior differential works is you simply take the exterior derivative of the components functions next to the differentials and you wedge with them. If you were to guess something, this would be the natural thing to guess once you had found this thing called the wedge product. All right? And we already know how to calculate these differentials. Like, what is dA? It's what? Partial xa dx plus partial ya dy plus partial za dz wedged with dx plus partial xb dx. I regret writing this, but I'm this far in, so I'm going to finish. Hey, at least this isn't a homework for you guys, right? I almost made this homework, but then I thought, you probably would benefit more from me just working it out in front of you as opposed to making this homework. Oh man, come on. No. dx, 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 no, no, no. What should I have there? dy. dz. I'm starting with omega is adx plus bdy plus cdz like I had over there. And I'm just exterior differentiating it. So I should have a dx here, but I should have a dy here, and I should have a dz here. So you've got 9 total terms, right? 3 of them are 0. Which ones are 0? So like dx wedge dx, 0. dy wedge dy, 0. dz wedge dz, 0. All right? And so I'm going to group things. I'm first of all going to keep my dy wedge dz, and then I'm going to keep my dz wedge dx, and then I'm going to keep my dx wedge dy over here. So the first, so where do you get yz's? Let's see here. dy dz is over here. That's partial yc. And then you get minus partial z b. For zx, I've got a partial za minus a partial xb, no, c, I think. Partial xc over here, but I got a dx wedge dz, but I have to flip it so I get a minus. And let's see, xy, I have partial xb minus partial ya. This is the flux form of partial yc minus partial zb, comma, partial za minus partial xc, comma, partial xb minus partial ya. This is the flux form of what? Do you know what this is? Relative to the vector field ABC? What new vector field has 6 terms in it formed by alternating sums of partial derivatives of the components, much like a cross product? Calc 3 is a prerequisite for this class, is it not?
It's been a while.
No one remembers? Oh. So this is the curl of the vector field ABC. So the exterior derivative of a one form, like, let me just put it more symbolically, the exterior derivative of a one form of a vector field f is the flux form of the curl of the vector field. So the exterior derivative automatically produces curl. What was the other thing we learned in Calc 3, differentiation-wise? One more thing, it was the divergence, right? So the divergence, I'll spare you the proof, but if we calculate the exterior derivative of the flux form of G, it ends up being the divergence of G times dx wedge dy wedge dz. So the exterior derivative, it always produces a differential form which is 1 degree larger than you started with. Okay, so that's the exterior. Now the exterior derivative satisfies really cool properties, like here's one. The exterior derivative of like alpha wedge beta, it ends up being d alpha wedge beta plus minus 1 to the degree of alpha wedge d beta. So there's a sort of graded product rule for the exterior derivative, which is a little bit different than the product rule you're used to, but that's how the product rule works for the wedge product. There is a product rule. But the thing that's actually very interesting is if you take the exterior derivative twice on any differential form, it's equal to 0. So the double exterior derivative is 0. It's been said that that single equation contains all the equations of physics. I think that's a little bit of an overstatement, but there's a lot to it. So like, to just give you an example of d squared equal to 0, if we take the exterior derivative of the exterior derivative of a function, that means we're taking the exterior derivative of the work form of a gradient, which is meaning we're having the flux form of the curl of a gradient. Perhaps you remember the curl of a gradient is automatically 0. That is one example of d squared equal to 0. There are infinitely many others. All right. I've shown you the exterior calculus in 3 dimensions, but it works in n dimensions. Unlike cross product, which is a 3-dimensional thing, wedge product you can calculate in n dimensions. This is the calculus that is most natural to curved spaces. So if you're studying like fluid physics, for example, plasma physics, this is the kind of thing you might end up needing to know. All right, let me go on here. So there are 2. Let's see here. I need to find a spot to write. So definition. A differential form is closed if let me give the name. Let me give the differential form a name. Differential form alpha is closed if d alpha equals to 0. A differential form is exact if alpha, I need to give it a name, alpha, is exact if alpha is equal to d phi, right, for some differential form phi. So you have exact forms and you have closed forms. So think about this. Since d squared is equal to 0, what's that tell us about, what's that tell us about exact forms? There's a theorem to say here, right? If if alpha is exact, then d alpha is what? It's actually d of d phi, right? Which is d squared, which I'm telling you, an identity of the exterior calculus is that's 0. So what this is to say is that exact implies closed. All right? But think about this. Let's get back to differential equations for a second. We were studying exact equations. What does it mean for an equation to be exact? What does it mean for the differential equation m dx plus n dy is equal to 0? This is exact when?
Partial n, partial y is equal to partial n, partial x.
Well, that's the closed condition. But exact technically means that this can be written as the differential of f, right? That is literally the definition that I should give you for exact equation. It's that it's the total differential of a function. If that's true, what is d of df equal to? It's equal to 0, right? But what else is it equal to? It's equal to dm wedge dx plus dn wedge dy, which is, in this case, partial x m dx plus partial y m dy wedge dx plus partial x n dx plus partial y n dy wedge dy. And what's that work out to? So like dx wedge dx is 0, dy wedge dy is 0. And we're just left with partial x, rather partial y, m, dy dx, plus partial x n dx dy, wedge dy, which I'll write over here. Man, rats. Stupid. Which is, partial xn minus partial ym dx wedge dy. Right? So how can this be 0? See, in order for this to be 0, we need that partial nx equals to partial ym. Right? We need that closed condition to hold. It actually is yet another aspect of this general equation that d squared is equal to 0. So, anyway, if you want to know more about like exterior calculus and how these things all work, if you come take my advanced calculus class, I will show you much more about this. Like, we have 2 minutes, so let me show you something else. There is something called this right here is the generalized Stokes theorem. The integral over the boundary of a manifold of a form is equal to the integral over the manifold of the exterior derivative of the form. This is the so-called generalized Stokes theorem. This single theorem reproduces the fundamental theorem of calculus Green's theorem, the divergence theorem, the Stokes theorem, all of it. Pretty much every major theorem you had in Calculus 3, it's all in this single statement. All right? How do you integrate forms? Pretty much you just drop the wedges. Like the integral of a 1 form is a line integral. The integral of a 2 form is a surface integral. The integral of a 3 form is a volume integral. All these concepts get tied together in one universal form language, if you're interested. Now this stuff is not that old. It's really the work of Cartan about 120 years ago, something like that. I don't know, ish. But hey, that's all I got for today. So next time we'll do like proper theory of differential equations, and we will, before you know it, be into applications. Not too long. So thanks, guys.